Hi everyone, my name is Krishna Karnamadakala. I'm a student at Colorado State University and I am taking this class with the help of Dr. Duan. My subject or the topic today is on my project on optimal phasor measurement units. As we all learned from class, phasor measurement units are devices that can measure both the magnitude and angle, referred to as the phase, of any quantity, any complex quantity. The advantage of these equipment, as discussed in class, is that they are GPS synchronized, and therefore when you're measuring phases from one point to another, you have a synchronized clock. They have a higher sampling rate, and as a result they provide better state estimation and stability study results. So there's an interest in us having in the electric grid more phasor measurement units. The challenge though is phasor measurement units and the necessary phasor data concentrators are expensive equipment. Some numbers that I found suggested that the cost and labor of installing a phasor measurement unit is around $43,000 per device, and having a phasor data concentrator is $107,000. Fortunately, you don't need too many phasor data concentrator for each. You don't need a one-to-one phasor data concentrator to phasor measurement. You can have one for many, but you will need some in order to use the phasor measurement units. The cost of the PMU itself is approximately a quarter of the numbers mentioned at around 11,000, and it's generally determined that upgrading them is cheaper than buying and installing a new equipment. So as part of my project, I was trying to find out, how do we install PMU but keep it to a minimum so that we don't have to add too much and still get good state estimation. And the authors, did their analysis on various bus sizes. I did my analysis on a 6-bus system. Now, as we've learned in class, with phasor measurement units, the equation becomes linear, and the way and it's a linear equation which I basically understand in very simple terms, saying that okay, if you have an input and a different input, and if they were individually result in an output, adding them together will result in an output that is the sum of the individual outputs. And in this case, basically we have 4 vectors, three vectors in the matrix. You have the z vector, which is the measurement values. This is the real-time measurement values that we would get from the phasor measurements, or any if prior to phasors they were just voltage transformers and things like that, real-time measurements. The x vector is the values that is to be state estimated, and since we want some, and the epsilon refers to some amount of error tolerance, and the H is the measurement matrix, where each row of the matrix H represents a measurement, a single measurement. Now for a 6-bus system, which was shown before, we're going to have, and the type of design that was there, I was going to have 28 measurements, 6 for each bus voltage, 6 for each bus's injection, and then there were 14 lines, there were 6 lines, so 6 times 2 is 12, so there were 12 measurements there. So in total I had 28. Then for the state estimation, we want to know the voltage phasors at each bus, and since there are 6 buses, you have 6. And then based on the construction of the bus that I showed earlier, these are all the measurements that I would want to see, or that's what we would like. Since the previous picture was really small, I'm showing you a slightly magnified but incomplete version of the matrix, and I had to build this matrix for the purpose of the project. So in order to find the optimal measurements, there are 4 steps. There is a sequential elimination, sequential addition, finding the optimal redundant measurements, and minimization of PMU placement sites. And I will go over each of them briefly to convey the idea behind it. This is the algorithm I created for the sequential elimination. Basically what this does is it takes the 28 by 6 matrix that I had, so 28 measurements by at 6 buses, and it reduces it down to the absolute minimum, which is it becomes a 6 by 6 matrix. This matrix will now solve this, just these 6 measurements basically. What this is saying is just these 6 measurements will solve and give you a state estimated result. The challenge is, though, if you lose even one of the measurement, then you're not going to get a solution anymore. So what do we do about this? Well, then we go through the sequential addition process. This is a code that I wrote for that purpose. And what happens with the sequential addition process is we start checking for contingency. If in that new H essential matrix where there were only 6 measurements, you had lost one, then among the remaining 22 measurements that we had originally removed, saying that we didn't need it to get the solution, well, which of these measurements when added will replace the one that is lost? And that is what is going on. And you're running through it for each contingency and identifying all the measurements that could replace the one single measurement that one single contingency that might occur. Well, this is great, but now you have a bunch of measurements again saying, oh, you have a bunch of measurements that could solve a single problem, and you want to minimize them, and preferably you want to find ones that will sort of overlap. Like if a single measurement could resolve multiple contingencies, you would want that rather than finding 2 separate ones so that you don't have to install multiple phasers. Well, this loop, the finding the optimal measurement using binary integer programming, will do that. Here we're doing a binary integer programming problem, and what we're doing here is we are taking all the measurements that have been added based on the contingency, and we are minimizing it to the measurements that you need that will ensure that if there is a contingency in the original, the H essential 6, then you have extra measurements that will ensure that you're still going to get a proper solution. But even this is not the absolute minimum, because what's going to happen is this will give you a solution, and it may say, hey, you know what, I think you should have a measurement at bus 6 for the line from bus 2 to 6. But you might already have measurements at bus 2, and a single phase measurement union can probably measure multiple devices at a particular substation. So you want to move it from bus 6 to bus 2, and that's what's going on here. So that's the last step that you need to do here. So I was able to implement all of these, and largely the success of my project is that I was able to understand this methodology. It was actually fairly confusing early on because I started this project before the professor had covered similar topics, and it was more challenging in the beginning, and maybe I'd have benefited from starting it much later, because then I would have known what the intent is. But I did manage to understand how phasers and what effect they have in our system and why they're important, and something that's useful because I work in a company that does use these devices. I was able to successfully implement the sequential elimination optimization of the redundant measurements, and I think I see that it can succeed slightly for slightly larger systems. Now, where I have need to do further research on is there's a threshold factor in the sequential addition algorithm, which I just picked a number, but I had no idea on how to make an engineering decision to determine the threshold. So I still need to do more research there. The other part of it is I do need to, although I say I think it succeeds for some larger systems, I know it works for 6 and 14 and 30 and even 60, but I have not been able to study it for 9,000 buses, and that's that's the size of the peak system, for example. So there still needs to be studies done there, see if it'll really slow things down. My conclusions are, one of the things is when I was doing the paper and I was redoing the results obtained by the authors, I found some differences in my paper, in the results of the paper versus my own experiment. They were similar but not exactly the same. So I question whether I'm challenging whether the author's notes were correct, especially because a lot of the things that they had written could be simplified and explained more clearly. I suspect that they may have made some errors, or I certainly not find any on my own. I need to make some engineering decisions regarding the threshold value, and I'm also trying to suggest a algorithm for minimization of PMU placement sites, because there isn't one. There's steps to do it, but right now we do it sort of manually. Well, I want to find out if there's a way to do it in an algorithmic system or a programmatic system. The other flaw in this methodology is that it assumes the labor and cost is the same everywhere, because we're doing an average system. But we may find that, it might be nice to put things in California, but labor and cost of things in California may be a lot more expensive, so you might as well as do it in Colorado or some other cheaper state. There is potential savings irrespective of how you do it, because for the 6-bus system, we determined that it might save, from a cost of 1.2 million, it might go to a quarter of that size, or a third of that size, I should say. The other concern I have is, despite the fact that this algorithm would work quite well with PMU placement and minimize it, this is not a situation where one company decides all of everything, and we may find that okay, we want to put so basically what we're trying to figure out is, okay, so we have all these measurements, but we may not want to stop there. We may decide, okay, this is fine for a particular scenario, but if we had new topological changes, those facial measurements would probably readjust, and this would not resolve that. Ideal solution, I think, is really to lower cost of PMU and labor for installation. And that is my presentation. Thank you.